Good afternoon, everyone. Those of you who have joined, today we are doing Faraday's law of induction. Faraday's law of electromagnetic induction, named, of course, after the famed English experimental scientist. Don't think we can call him a physicist yet, but I think we could call him a physicist, Michael Faraday. Okay, so let's look at some of the questions, okay, that we've been given regarding Faraday's law. But before we get there, let's just look at what is Faraday's law. Okay, what does Faraday's law entail? What does it say? And all of that. Now, Faraday's law states the following. Okay, it is 12 o'clock now, so yes, I can begin. Faraday's law states the following, that an induced EMF is given by the negative of the change in the magnetic flux, over time. That is Faraday's law. It simply states that an EMF is induced when there's a change in the magnetic flux over time, with the magnetic flux being given by the following formula: B dot A, the integral of the magnetic field dotted with the area. Okay, change in the area. So that is Faraday's law, and this is magnetic flux. Now let's look at question number 1. They tell us an EMF is induced. An EMF is induced, or rather, an induced EMF is produced. An induced EMF is produced in. Then they give us options. Okay, A, B, C, D, E. Okay. So let's look at each option and we'll say yes or no if or if there is an EMF induced. Okay, let's look at number A, or rather A. Okay, a closed loop of wire when it remains at rest in a non-uniform static magnetic field. Will this induce an EMF? A closed loop of wire, so we have a closed loop of wire in a non-uniform, meaning the magnetic field looks something like this. When it remains at rest, so the closed loop of wire is not moving through this magnetic field. Okay, so relative to each other, the magnetic field and the area, the closed loop of wire is at rest with regards to each other. Now, in this scenario, okay, the magnetic field is static. They tell us that it's non-uniform static. It means it's not changing with time. Okay, so the magnetic field is not changing with time. Okay, so dB is equal to 0. Okay? The change in the magnetic field is equal to 0. Okay, so the magnetic field is not changing. So if the magnetic field is not changing, then the flux, we can write flux as B times A. Okay, so if the magnetic field, the change in B is 0, if there is no change in the magnetic field, then the flux is 0 if there is no change in the magnetic field. Okay, so if the change in magnetic field is 0, the flux is zero. And if the flux is zero, the induced EMF is equal to zero. Okay? Because if although the field is like non-uniform, it is changing as you move along the field. The magnetic flux through that surface is remains the same. The magnetic flux remains the same because neither the field nor the loop's position relative to each other is changing. Therefore, the change in the magnetic flux over time is zero. So no EMF is induced. No EMF. So no EMF induced in A. What was the question? An induced EMF is produced in. Okay, so there's no EMF produced in A. Let's look at B. A closed loop of wire, okay, when it remains at rest in a uniform static magnetic field. So we have a closed loop of wire, we have a magnetic field, uniform. These two are not moving relative to each other, so the magnetic field is not changing. Or rather, let me say this. There is no, the magnetic field is not changing over time. The area is not changing. Therefore, the magnetic flux is also zero. And if the magnetic flux is zero, then the EMF induced is zero, meaning there is no EMF induced. There is no EMF induced. Okay? No EMF induced in B. Let's look at number C. Okay, we have a closed loop of wire. Okay, so we have a closed loop of wire moving at constant velocity in a non-uniform static magnetic field. So we have a closed loop of wire and a non-uniform magnetic field. Okay, as this loop of wire is moving, the magnetic field is changing. So dB, the change in the magnetic field over time, is not equals to zero. And if that is not equals to zero, the area stays constant. And if the dB is not equal to zero, then the change in the flux, the magnetic flux, is not equal to zero, meaning there is no, the EMF induced is not equal to zero. So there is definitely an EMF induced in C. So EMF induced. So there's an EMF induced in C. So C is the correct answer. Let's look at B. All of the above can't, because A and B does not induce a magnetic field, and does not B does not induce the magnetic field. So only C is correct. Let's check. Your answer is correct. A closed loop of wire moving at constant velocity, and here is the kicker. If it was moving at constant velocity in a uniform magnetic field, it would have been a different stage. But the magnetic field is non-uniform, meaning the magnetic field is changing over time, and any change over time means there is a flux, a magnetic flux. So if there is a magnetic flux, then an EMF is induced. Okay. So to the students listening, welcome. I hope you understood that part. So we have a flux that is induced. Question number 2. Remember what Faraday's law is, correct? Faraday's law states simply that an EMF is induced if there is a change in the magnetic flux over time. Now we know that magnetic flux is equal to magnetic flux is equal to B times A. in its simplest terms, but in actual fact, it's magnetic field dot dA. Okay, so if the area or the magnetic field changes, a flux is induced. So one of the two must change in time for a flux to be induced. So if the area changes, flux is induced. If the magnetic field changes, flux is induced. If both of them change, flux is induced. Well, not induced, there is magnetic flux. Then an EMF is induced rather. Question number two. For which of the following is an EMF induced? Let's look at A. For which of the following is a EMF induced? A, B, C, D. Okay, for which of the following is an EMF induced? Let's look at the first one. Okay, they tell us a conducting rod in red. Okay, that's the conducting rod there in red. A conducting rod is pulled on a conducting rails. Okay, so we have a resistor there, and then we have the conducting rails running parallel horizontally, and then the conducting rod red. And in red, those two, those they complete a circuit rather. Okay, a circuit of rectangular shape. Okay, remember a square is also a rectangle. Okay, so a conducting rod is pulled on conducting rails that are placed in a uniform magnetic field. Okay, on a uniform magnetic field directed into the plate. So the magnetic field is constant. Okay, so B is constant. The magnetic field is constant. Okay, now remember, flux is equal to the product of the change of B times A. Okay, the product of magnetic field, I should write it like that. Okay, the change of magnetic field times area. So if either one of those two changes over time, then there is magnetic flux. Okay, so in the first one, does the magnetic field change? No. However, the area in the first one does change. The area changes because as that rod is sliding, the rectangle is either getting bigger or smaller, meaning, and the magnetic field stays the same, but the area is changing, meaning there is an electric flux, a magnetic flux, sorry, magnetic flux. And if there is magnetic flux, a change in the magnetic flux, and if there's a change in the magnetic flux over time, there is an EMF induced. So there is an induced EMF. Okay, for which of the following is an EMF induced? I will just say there EMF induced. So in number one, the area changes over time, which means the magnetic flux changes over time, which means there is a magnetic an EMF induced. Okay, look at B. Okay, let's look at number B. What is happening in B? Let's look at the description of B. A conducting loop moves through an uniform magnetic field directed into the page. A conducting loop. A conducting loop. Okay, so this loop is moving in a at a constant velocity. It's moving throughout this magnetic field. This means that as it is moving, the amount of electric field lines going through that loop stays exactly the same the whole time. And since it's moving at a constant velocity, the magnetic flux, the change in the magnetic flux is zero, okay, over time. And if the change in the magnetic flux is zero, there is no EMF induced, no EMF induced. I'm going to just write no EMF IND. No EMF is induced in B because the amount of electric field lines going through that rectangular shape is constant as it is moving at a constant speed. Okay, C, we have in the lower left corner, C. Let's just look at the description. We have a conducting loop rotates, okay, about an axis perpendicular to B field, okay, to the magnetic field. in a uniform magnetic field directed into the page. So there we have the magnetic field highlighted by or depicted by these circles. So we have the magnetic field there, and as that magnetic field is rotating, or rather as that conducting loop rotates, as the loop is rotating, the area through which the magnetic field lines go through is changing. Okay, remember the loop looks like this. Sorry, at its widest it looks like this when you're looking at it full on. But as it is rotating, its size may change. It may get smaller as it rotates, smaller until eventually you only see the top side. Okay, so only this is visible because it's rotating. So in this case, the area is changing, and if the area changes, the magnetic field is still constant, but the area is changing, and if the area changes, there is a change in the magnetic flux. And that is always what we look for. You look for a change in the magnetic field, or you look for a change in the area. And if one of them changes over time, there's a change in the flux. And if there's a change in the flux, an EMF is induced. In this case, the area is changing, which means there is a change in the magnetic flux, which means there is an EMF induced. So EMF induced in C. EMF induced. Number D. Let's look at D. Is there an EMF induced? Look at D. Okay. There is a current carrying wire, and there is a resistor there, and the resistor is moving at a constant velocity, I'd assume. A conducting loop moves in a magnetic field produced by an infinite current carrying wire. So the magnetic field is changing as you move away from that wire. Okay, as you move away, they do not say it's moving parallel. So as you move away from that wire, the magnetic field strength changes. Remember, the field strength, the farther away you are from the current carrying conductor, the weaker the magnetic field, which means as you move throughout the magnetic field, the magnetic field will change, and if the magnetic field changes, there is a flux. There's a change in the magnetic flux, and if there's a change in magnetic flux, an EMF is induced. So an EMF is induced. If they specified, however, that conducting loop moves parallel to that line, then there would have been no change in the flux because the magnetic field would have stayed the same and the area of that loop does not also stays the same, so there would have been no induced EMF. But since they don't specify that there is a change in the, they don't specify that it's parallel to that conductor, that current carrying wire, so therefore an EMF is induced. So an EMF is induced in A, in there's no EMF induced in B, but then in C and D. So A, C, and D. Okay, A, C, and D. Let's see if there's an option for A, C, and D. Number 5 says A, C, and D only. Let's check. Yes, it says there beautifully, correct. There is an EMF induced in A, C, and D only. I hope you understand why there is an EMF induced in each one of them. Let me just recap. There's an EMF induced in number A because the area is changing. In B, there is no EMF because both the magnetic field stays the same and the area stays the same. And in C, the area is changing through which the magnetic field is running through. Remember, we only look at the perpendicular section of the area. And then here in D, the magnetic field is changing the farther you go away from the current carrying wire. So, question number 3. This is going to be quite quick today. Question 3. The figure below is a graph of magnetic flux through a certain coil of wire as a function of time. Okay, so magnetic flux is a function of time. So let's just look at that. Let's just look at some graph. Just going to draw some random graph. Here's magnetic flux, and here is time. Okay, so and there is the graph. So the slope of this thing the slope of this graph, the slope of a graph of magnetic flux versus time is going to be equal to the slope is going to be equal to the change in magnetic field, the change in flux, excuse me, over the change in time, and that is equal to an EMF, okay? Equal to the negative of an EMF, basically. I should say technically it's equal to the negative of the EMF. So it's equal to the negative of the EMF. So the negative of the slope is equal to an EMF. So if the slope is zero, there's no EMF. Okay? They ask us now. It doesn't matter what graph it is here. I just drew some random line thingy just to show you that the slope of a graph of magnetic flux to time is going to be equal to the EMF. Now, now the graph shows magnetic flux through a certain coil of wire as a function of time during an interval while the radius of the coil is rotated through 1.5 revolutions. That is not important. Okay, and the external source of the magnetic field is turned off in that order. Okay, so well, it is important, but not when you want for this particular question. Okay, which of the following is true about the ranking of the EMF induced in the coil at the instance mark A through E? Okay, so you need to tell me at what point, or rather, you should tell me how each one of these magnetic fields or these EMFs of these induced EMF rank in relation to one another. Okay, so the negative of each one of these slopes will give you the EMF. Okay, so the EMF induced in one in A, the EMF induced at that point in that section of A, right where A is. If you go down to the graph, the EMF induced there, the slope will be negative, so the EMF is positive. So we have A. We'll see now where it fits in. So the EMF is positive. This one here at B, at point B, the slope is zero because the line is horizontal. There is no change as the time is changing. The flux stays the same. So the EMF is equal to zero. So at B, so here it is positive. Sorry. At A it is positive. At B it's equal to zero. At C, the flux, the slope is negative. The slope is positive, but we're looking for the negative of the slope. So the flux is negative. Then at D, the turning point is zero again. The slope is zero, so the EMF is zero. And at E, that slope at E, at point E, is higher than the slope at point A, so it is positive, but it is bigger than A. Okay, so if we were to rank these, okay, if we were to rank these, let's say from the biggest to the smallest, or let's say biggest to smallest, okay, we would start with E, which is the highest negative slope, and then A, so it would be E, which is bigger than A, which is bigger than B, which is equal to B is equal to D, which is equal to 0, which is bigger than C. Okay, let me just rewrite that. A, B, D. So it's E, then A, then B, and D, which is equal to 0, and then C. Let's see if there is something in that order. Okay, which of the following is true about the ranking of the EMF? They don't tell us how to rank them. Okay, let's say E bigger than A. We have that, yes. Bigger than B, which is equal to D. We have that, which is equal to 0, which is bigger than C. We have A. Okay, we have that exact ranking. Uh, and none of the others. Let's just check our working of it. And your answer is correct. We are correct indeed in our ranking of these EMFs. What you just had to look out for in that particular problem is that the slope would be the EMF. So you have to just look and compare it to the slope. So moving on to question number 4. Are there any questions? If there are any questions, you can ask. If not, I'm going to continue. Question number 4. A circuit consists of a conducting movable bar. Okay, so this is the circuit, and here is the conducting movable bar completing the circuit, and there is a light bulb there. Okay, and there is a light bulb connected to the two conducting rails. So there we have two rails and then a conducting bar that can move, and it's shown in this figure. Now, an external magnetic field is directed perpendicular to the plane of the circuit. Which of the following actions will make the bulb light up? So, what will make this bulb light up? And it says there more than one statement being correct. Let's look at this thing. Okay. So let me just quickly redraw it. We have the two rails. We have the two rails. We have the bulb there. What will make the bulb light up? And then of course we have the movable conductor. We draw it there in red, completing the circuit. Looks ugly. Let me try to, oh, even more ugly. Let me steady my hand here. A bit better, not by much. Okay, so here. Okay, so when will an EMF be induced in here? Okay, when will an EMF be induced? I'm going to use red for this now. When will an EMF be induced? Okay. The only way this bulb will light up if there is an EMF induced, and an EMF is induced. An EMF is basically a voltage, and a voltage will light up the bulb. Okay, so when will this bulb light up? This bulb will light up when the area changes or the magnetic field changes. Now the magnetic field is not going to change. Okay, the magnetic field is not going to change. Or rather, let me just not say that. So when will this bulb light up? It will light up when the magnetic field going through the space changes, meaning the magnetic field is changing, or when this bulb is moving towards the left. What color am I using now? Why am I using white? Okay, okay. When this bulb is when this conductor, okay, when this movable bar is moved towards the left or towards the right on these rails, the, okay, do you have a question? Let me just see. Azola, you can ask the question.
No, like I want to interpret like this scenario.
Okay.
I think we should just like apply a force to this black completing the circle to the right, so that like on the left the area will increase, meaning the flux will increase. Therefore, on the left, according to Lenz, on the right, if the flux increases, we will oppose. So the current must go up in both sides. According to Kirchhoff's, it will go down along this road. So it will just circulate from going up, going down, and then completing the circuit. Therefore, the potential difference will be used to light the bulb.
Yes. That's what basically what I'm saying here. If we move this thing, if we move the conducting bar, there will be an EMF induced. It doesn't matter which way we move it. If the area changes, if the size of this area here, this area size changes, then an EMF will be induced. Because remember, flux, magnetic flux, is equal to B times A. So if either, or rather the change in B times A, the change in B times A, meaning if you change one of these things, if you change either the magnetic field or the area, a flux will be induced. Is that, do you understand that part at least as well?
Yeah, but I think the magnetic field is constant. We can only change the area.
Remember, we have not looked at what they asked. They just asked us which of the following. I'm just telling you guys right now. If we move that bar, the flux will be induced. Make EMF will be induced. The flux is going to change. EMF is going to induce. The second thing that will change, that will induce an EMF, is if we change the strength of the magnetic field. Those are the two things that will change or will induce an EMF. Now we go look at actually what they ask. Remember, the question is not done. They said which of the following actions will make the bulb light up. Now we go to the actual actions. Before we got there, I just told you, based on what we know, if the bar moves either way, it doesn't matter which way it moves, flux will change. If the magnetic field strength changes, flux will change. Okay, here's the options now. The magnitude of the magnetic field is decreased. If the magnitude of the magnetic field is decreased, a flux will be induced because the magnetic field changes. If the bar is moved to the right, the flux will change, meaning an EMF will be induced. That's A and B. If the magnitude of the magnetic field is increased, the flux will change as well, so an EMF will be induced. And if the bar is moved to the left, the area changes, meaning the flux will change and an EMF will be induced. And number E, if the bar is lifted off the rails, no flux, no EMF is induced. The bulb will not light because the circuit will be broken. So is which of the following actions will make the bulb light up? A, B, C, and D will make all of them will make the bulb light up because A causes the magnetic field to change, B causes the area to change, C causes the magnetic field to change, and D causes the area to change of the loop, and then D just closes off the circuit, meaning the bulb will not burn. So let's check A, B, C, D, and E. And it says my answer is correct. A, B, C, D, and E. Mr. Azola, do you understand now? Okay, I see you clapping hands there. Cool. So, before you even start a problem like this, just look at, based on your knowledge, what's going to happen if you move the bar? What's going to happen if you change the magnetic field? And from there on, I just went to the question. Okay, question number 5. Let's look at question 5. Oh, I'm writing in red now. Second to last question. I think this is one of the few that is actually a calculation question. Question number 5. There's not a lot of them here. Unfortunately, in uh, Faraday's law, well, not unfortunately, Faraday's law, a lot of it is there is very the calculations are very simple. Okay, fortunately. Okay, so let's say they tell us here a flat coil of wire consisting of 20 turns. Okay, so we have a flat coil of wire. It has 20 turns, each with an area of 50 square centimeters, is positioned perpendicular to a uniform magnetic field. Basically, this is what we have here. We have, is it circular? They don't tell us if it's circular. Okay, so it doesn't matter either way because they gave us the area. Then we have the magnetic field going in, perpendicular to this wire. Okay, so we have the magnetic field going in. And of course, there is like 20 loops of this wire. Oh, let me rather not do that. There's the first, the second one. My 3D drawings. Let me rather just do this. It should be easier to just do this part. Or In my head, it was easier. I'm not going to be able to draw all of them, but suffice it to say, there are 20 loops behind this one. Okay, this is one loop, and there are 20 loops behind them. Okay, if I had a ruler, I could draw it beautifully, but that is not the case. I'm pressing on a perpendicular screen here. Okay, so and it's positioned perpendicular to a uniform magnetic field that decreases its magnitude at a constant rate. Okay, so the magnetic field is changing from 2 Tesla to 6 Tesla in 2 seconds. Now, if the coil has a total resistance of zero point 0.4 ohm, what is the induced current? Okay, first of all, what do we need to know? Okay, how do we calculate uh, EMF? First of all, we need to calculate the EMF that's induced. We want the current, so we need to first calculate the EMF, or the voltage rather. Okay, so the EMF induced is equal to the number of turns in the coil. You should remember this formula, multiplied by the area times the change, or let me write it this way, the generalized form, the change in the magnetic field times the area over the change in time. It can be the change in either one of these. Whichever one is constant is just pulled to the front. Now we know that the area is constant. Okay, the area is constant. So we can pull that out. So it will be the number of turns in the coil times the area times the change in the magnetic field. Remember, the area does not change, it's constant over the change in time. And then we have a formula to calculate the induced EMF. Okay. Now, how many numbers of turns or number of turns in this coil is there? There is 20 turns in this coil. Okay, there's 20 turns in this coil. What is the area? The area is 50 square centimeters. Now, if you want to convert 50 square centimeters to square meters, uh, just remember this. 1 square meter is equal to 10 to the 4. Or you don't need to remember, you can just work it out. Okay? Just work it out. I used to teach dimensional analysis. By now, you should be very good at it. You did it in your first semester. 1 square meter is equal to 10 to the 4 square centimeter. Okay? So if you do that correctly, you should get that your area is 50 centimeters, just 0.0512. Is it? Yes, 0.05 square meters. Square meters multiplied by the change in the magnetic field over the change in time. The change in the magnetic field over the change in time. Okay. What is the magnetic field's change? It goes from 2 Tesla to 6 Tesla. So it's 6 Tesla minus 2, 6 Tesla minus 2 Tesla. And it does that in 2 seconds. And that, ladies and gentlemen, is the amount of EMF that is induced. Okay, it's the EMF that's induced. And EMF is also just voltage, so zero point 0.2 volts. That's the EMF that is induced in this loop. Okay, so this 20 turns of coil wire, this coiled wire, basically a solenoid. You can ask.
Is like the induced EMF should oppose the direction of the magnetic. Like, why is it positive here if it's from the external? Like, it's opposing, it's like the increasing flux.
The flux is, yes, the change in the flux is increasing. The change in flux is positive. The final is higher than the negative. What is the question? Let me get this.
The negative, why is it positive? The induced
Oh, the positive here.
is
Oh, this is just for magnitude's sake. Remember, we are not really interested in the direction of this or the voltage in this case. But in actual fact, yes, it does say negative of that, the EMF. In some examples, that is a good question. In some examples, you will have that the EMF is equal to the negative of n times that times the change in flux over time. Some people omit it because we are only interested in the magnitude, the numerical value. We don't care about the sign. Okay, the sign does play a role, but in this case, we are not actually interested in. But if you want to be uh, scientifically accurate, yes, it should be negative zero point 0.2 voltage. Voltage. Okay, so now remember, we are not asked to calculate the induced uh, EMF. We are asked to calculate the induced current. Remember, this is an induced EMF, meaning there is a potential difference induced and a potential difference if you run it through a resistor will create a current. Okay, so we then know from Ohm's law an induced EMF is equal to the current over the resistance. We have been given the resistance of zero point 0.4 ohm. First of all, let's make induced current the subject of the formula. So it will be, oh, sorry, I rewrote this. This is wrong. EMF is I times R. So the induced current is E over R. And if I can remember correctly, zero point 0.2 volts. I'm just using the magnitude here, zero point 0.2 volts over zero point 0.4 volts. And that is just half, okay, of that. So it's zero point 0.5 amperes, okay, just zero point 0.5 amperes. If you were to be very strict, you would write the negative there. This will be negative amperes. That will just indicate the direction of your current. But I rather choose to leave it out. Okay. So your final answer, zero point 0.5 amperes. Let's check if there is an option. There is zero point 0.5. Let's check if it's correct. Yes, it is correct. Okay. So this is mostly the type of problem you will get. That's why there is not a lot of them. It is like they will all revolve around this type of problems. Okay. And then I think the second to last problem, there is only 7 questions. So number 6 and 7. 6 is also calculation. And then 7 is using, I think, Lenz's law. And then that's it for today. So let's look at question number 6. It says the coil shown in that figure has two turns. So let's look at it. N is equal to 2. This is what I always like to do. Whenever I see something, I start writing it down, all the information. Right? So N is 2, a cross-sectional area of zero point 0.2 meters. So the area is zero point 0.2 meters, zero point 0.2 square meters, excuse me. And a field parallel to the axis of the coil. Okay, there's a magnetic field that's running through the coil. It's parallel to the axis of the coil, meaning it's running. Is given by B, and here is one of the other ways they can ask this, and I actually like this part because it tests your derivative skills. Okay, 4.2 T. Oh, that's not T. This is a non-uniform magnetic field. This is what a non-uniform magnetic field looks like. Okay, it's changing over time. Okay, and it's in Tesla. This magnetic field is changing over time. Okay, after 1 second, this magnetic field is 7 Tesla. But after 2 seconds, if you plug 2 in there, that's 2 squared, that's 4 times 3, that's 12 plus 4, that's 16 Tesla now. Okay, you get that? Uh, so the magnetic field is changing as the time changes. Okay. What is the potential difference? They want the potential difference V minus Vc at time equals to 3 seconds. After 3 seconds, what's the potential difference? Okay. So, first, let's find the change in the flux, or rather, not the flux, the change in the magnetic field with time. Okay. dB dt. It's the change of the magnetic field with time. Okay. So basically, you're finding the time derivative of the magnetic field, which is 4, comma 0 plus 3, comma 0 t squared. So if we find the derivative, we get 6t. Is that correct? So the magnetic field, the derivative is 60. Okay. Now, of course, we need to multiply it. Just check here. Okay, point 0.2. Yep, yep, yep. Okay, so it's 60. So there we have dB dt. Okay, now let's calculate the change in the flux, or the change in magnetic flux, or rather the EMF. The EMF then is equal to N. I hope everyone understood you can do this in two ways. Number one, you could have done it here by multiplying this whole thing by N, which in this case is 2. Oh, that should not be 60, it should be 6. By N and the area, of course. You then multiply by the area as well of zero point 0.2, so you will get the whole flux. But in this case, I just calculated dB dt. Okay, so this is magnetic flux. It's the magnetic. We write it in the formula the way that we just wrote it. dB times A. This is the way we wrote it earlier on. But the only difference is we used delta instead of D. It's the same thing. So N in this case, it's 2. N is 2. It's 2 turns, if I remember correctly. Let me just check and make sure. 2 turns, yes. The area is constant. The area is not changing, so the area can come outside. The area is zero point 0.2 meters. The magnetic field is changing with time, and that change with time is 6.0 T. That is the magnetic field. So that is zero point 0.4. Let me just calculate that. I'm going to show you on the calculator. It's 2 times zero point 0.2 times 6. It's 2.4. So the answer then for the magnetic field is 2.4 T. Okay, that is the induced EMF. It's 2.4 T. Okay, that is the induced EMF, 2.4 T. Okay, hopefully everyone can get there. It's not that difficult. So now that we have the induced EMF, okay, they want, remember what they want. We have that the induced EMF is 2.4 T. Okay? They want VA minus VC. This is what we want. We have the induced EMF, and they want it at a specific time after 3 seconds, I think. Let me look at that. Yes, at time equals to 3 seconds. What is the EMF induced at time is equal to 3 seconds? So we calculate it at 3 seconds. So the EMF at 3 seconds or after 3 seconds or at exactly 3 seconds is equal to 2.4 times 3. Remember, it's negative. I forgot it's negative E. That is negative 7.2 volts. That's the EMF. That's the EMF that is induced. Okay, negative 7.2 volts. And if you look here, they want the potential difference between A and C. Okay, so the potential difference between A and C. Okay, and that potential difference is nothing but the induced EMF. It's the only thing that's creating a potential. There's no battery in there. So VA, the potential difference between A and C, is equal to negative 7.2 volts. Okay, negative 7.2 volts. Negative 7.2 volts. Uh, I think Mr. Azola earlier on reminded me that I should never forget that negative. Okay, if you were to have forgotten that negative, you would have gotten an answer correctly as 7.2, but it would have been positive, but your answer would have been wrong. Okay, because it's always the negative of that value, the negative of n times the change in the magnetic flux. Okay, the last question for today. I hope everyone understood that one. If you did not understand, please let me know now before I continue with the next one. The last one. Okay, question number 7. It's the last one. A straight conductor lies in a horizontal surface. Okay, with two coils of wire on either side. So here's the conductor, and there's two coils on each side, one on east and one on the west. Okay, as shown. Okay? The current in the conductor flows from south to north. So basically it flows northwards in short. And it is decreasing in magnitude with time. So the current is decreasing. Okay. When looked at from above, the induced current circles are. So if you were to look at it from above, okay, at the current in the east and the current in the west, in the east coil and the west coil. This is the west coil and the east coil. Okay. In what direction would the induced currents flow? Remember the magnetic field, the electric current is flowing from south north and it is decreasing. The current is in decreasing with magnitude. Okay, and if the current is decreasing with magnitude, over time the magnetic field is changing. And if the magnetic field is changing, then an EMF is induced. And if an EMF is induced, according to Lenz's law, that induced current in the coil will flow in a direction that opposes the change in the magnetic flux that produces it. Okay, so let's look at it. Okay, okay, yeah, go ahead, ask Mr. Azola.
No, like I think like according to Lenz,
Mm-hmm.
if the current is decreasing, we support.
Yes,
So in this case, if they're saying the current decreases, meaning also the flux,
yes.
like the flux decreased initially before the current decreases. Therefore, we must induce a current that must support the decreasing current.
Not support. It must oppose it.
If it's decreasing,
Then we must create a current that is increasing the flux, according to Lenz's law. Remember, Lenz's law will create a current that opposes the what had just happened. Okay, so if we create a current that causes uh, the magnetic field, or we induce a current that flows clockwise, or rather, if the let's say that we have a decreasing current, okay, and that induces a change in the flux, okay, which induces an EMF in another wire, okay. That
Yes.
EMF that is induced in that other wire will be created in such a way that it opposes the change that brought about the EMF. It's always trying to negate the effect of one. So let me just show you an example. Let's say we have a current here. There's a wire carrying there, and then we have a coil here, a square coil. There is a magnetic field around this wire, and of course it changes. Okay. Now, according to say Lenz's law, if this wire induces an EMF, okay, that EMF will induce a current because it is a voltage, okay, and if this voltage makes the current flow say anti-clockwise, okay, that what determines basically Lenz's law allows you to determine the direction of that induced current, okay, because that current that must be created, okay, because of that EMF must flow in the direction that will oppose the creation of the current in the first place. Let's say this magnetic field induces a current, an EMF that makes the current flow counterclockwise, okay. This counterclockwise will create its own magnetic field, and that magnetic field will will oppose the change in the magnetic flux that causes this thing to flow clockwise in the first place. Does that make sense? Basically, Lenz's law says whatever change, whatever magnetic flux change you do will create some current, and that current will try to oppose what you just did. Okay, so let's look at this problem. Maybe you will understand it better. Okay, so it's kind of difficult to explain what just I need some good images. So let's look at this thing. So we have a current that's flowing. We have two circles. We have a current that's flowing northwards. We have a coil in the west, and we have a coil in the east. We need to determine the direction of the currents in these two. Okay. So according to Lenz's law, the current in a coil, so the currents that were induced in these two coils, right, will oppose the change in the magnetic flux. Okay. So let's look at what is the change in this magnetic flux. It says here the current in the conductor flows northwards and decreases in magnitude with time. Okay, so the current decreases in magnitude with time. So if this current in this wire is decreasing, okay, it's decreasing. I just looked at it as increasing. It doesn't matter. So if it is decreasing, it is creating, well, normally without looking at increasing or decreasing, this current is creating a magnetic field around it, right? Okay, so it's creating a magnetic field around it. Now if it is increasing, it will create a magnetic field that is counterclockwise when viewed from above on this current. Let's say this is the current, this is the wire. If you were to look above at the wire, if the current increases, okay, if the current increases, that means the flux is increasing, so it will create a magnetic field around it if it's increasing, but they don't ask for increasing here. It is decreasing, so the current is decreasing, so the electric field, so the magnetic field around it will be clockwise. Okay, the magnetic field around this wire will be clockwise due to that change in the current. Okay, if it decreases, it will create a current, a magnetic field around it that is clockwise. Okay, so if we have created now a magnetic field around this wire that is going clockwise, okay, that magnetic field will go through It'll change constantly because it's changing with time. It'll go right through these two loops and it will induce an EMF. Okay. Now, when it induces an EMF in these two loops, the currents in both of these loops will create a magnetic field of their own, which must oppose this magnetic field. Okay. By the way, this magnetic field is determined by the right-hand rule, or the flux, the law of flux. There is a section there on it. Now, these two, there's a change in flux, which means an EMF is induced in the east coil and in the west coil. Okay? And both of these will create their own magnetic fields. Those currents will create their own magnetic fields, which will oppose this magnetic field. Okay. Now, to oppose the counterclock or those clockwise magnetic field from the straight wire, this induced current in the coils will circulate in the following way. In the east coil, they will go counterclockwise to oppose it. To oppose this magnetic field, this coil will create a or will induce an electric field going counterclockwise, because if you go counterclockwise, the magnetic field that is created, if you were to go counterclockwise, the magnetic field that is created will go in this direction, in a counterclocks direction. Okay, if you use the right hand rule. Okay, if you were to point your thumbs in the direction of counterclockwise, it will create a magnetic field that will oppose the magnetic field created by that one. Now this one therefore must create a magnetic field in the opposite direction. Okay, so the current will be flowing, of course, in the opposite direction, clockwise. Let me just make sure that's correct. Yes. Basically, you just need to check which one, what is the direction of the main conductor, and then what directions will oppose it. Okay, in this case, the main one will have a clockwise magnetic field from the straight wire. Okay, meaning this one must create a counterclockwise, and that one must also create a counterclockwise. A current that's creating counterclockwise. So the correct option is clockwise. Let me just see. Did I do this correctly? If we were to go clockwise, it will go that way and oppose it. So clockwise in the east coil, clockwise, it's going down. Oh, I'm using my left hand. So clockwise, let me see, that way. So it's going into and out. So this is wrong. It should be clockwise that way, and this one should be counterclockwise, obviously, to oppose that one. So clockwise and counterclockwise. So clockwise this way in the east one, and counterclockwise in west. Clockwise in the east coil and counterclockwise in the west. And yes, I did do it earlier. There was a nice drawing I had earlier to just remind myself. Let me just see if I can find. I don't know if I can find it, but before I go any further, that is done by the way. But I'm going to check something. I want to show you something. It's about Lenz's law. Maybe you'll understand the problem better. Okay, so yeah, this is the notes that I checked. Okay, so Lenz's law basically says, okay, any induced current. Okay, so if we have a coil, remember Faraday's law says if there's a change in flux, there will be an induced EMF. Okay, now any induced EMF creates a current. Now Lenz's law helps you to determine the direction of that current. Will it be clockwise or counterclockwise? Okay, so that's what Lenz's law does. It helps you determine the direction of that current. So, Lenz's law basically states any induced current in a coil, okay, will create a magnetic field. We all know that moving charges create magnetic fields. So, any induced current will create a magnetic field. Let me see if I'm sharing this. Should be okay. Yes, there it is. It's up there. Remember, I also study like this. So it says Lenz's law states any induced current will create a magnetic field that opposes the change in the magnetic flux that causes it. Remember, there must be a change in magnetic flux to create a EMF in the first place. Okay. Now, if the EMF is created, it induces a current or creates a current. Now, that current will induce its own EMF that opposes the change in will create a magnetic field that opposes the original change. Okay. Uh, Basically, there is a small. I think it was Volta who said nature abhors a change in flux. So whenever you create a change in flux, nature will create a basically it will create a current somewhere. It must be in that coil. Basically, it will create a current that changes that opposes your change in flux. So if you decrease the flux, a current will be created that must increase the flux. Does that make sense? Okay, to you guys that are still listening, does that make sense? Mr. Zola, you still there? We spoke about this earlier. Okay, so nature will always try to create a change in flux that opposes your original change in flux. So here's it, a simple breakdown. So a change happens. Number one, a change happens. So a changing magnetic field is applied to a conductor. In this case, we change the magnetic field or wire. Okay. This induces a current in that wire. Okay. Now, this electric current will create its own field. Okay. Now, this field that is created, this magnetic field that is created, must oppose the original magnetic field. It must always be in the opposite direction. That is how Lenz's law works. And then, of course, there are many examples, but if you were to look at this one that we just did, okay, we have the current flowing upwards. Okay, if you use uh, your right hand rule, point your thumb in the direction of the current moving. Okay, you will see you will create a magnetic field that is going. Let me check. It's going counterclockwise, correct? It's going counterclockwise. You're creating a magnetic field that is going counterclockwise. Okay, so now you have a magnetic field going counterclockwise. Okay, I hope you understand it. Point your thumb in the direction of your right hand rule, your right hand, the thumb of your right hand, pointing in the direction of north or the direction of the flowing current. It will create your, and then close your fist like this. Let me see if I can, am I still on the camera? Okay, so you have your right hand like this, still behind, let me see. So you have your thumbs up like this. Your thumb will point in the direction of the current, and your curled fingers will point in the direction of the magnetic field. Now, that just shows you that the magnetic field that you just created in that wire is going counterclockwise. Now, in those two if you have the two other circles, so you have just established that you have the current going this way, your thumb is pointing in this direction, north, and then your curled fingers is pointing in this direction. So now the you have a magnetic field. You just created a magnetic field that is going counterclockwise. Now those two coils here, the one here in the east and the one in the west, they must create magnetic fields that oppose this one. Okay, so you know the magnetic field going in this one must be opposing, so it must be that way, and the magnetic field in this one must be that way. Okay, there you immediately know the magnetic fields that must be created must oppose them. Okay, so that's only the so you might mistake that for the direction of the current. That is the magnetic field. So the magnetic fields for these two must be, the magnetic field for this one must be counterclockwise, and the magnetic field for this one must be clockwise. Am I right? No, for both of them must be counterclockwise. The magnetic field. They must oppose. Yep. Yes. The magnetic field for both of them must be counterclockwise. Now, how do you create a counterclockwise magnetic field in this one? Okay. You use the right hand rule to determine which direction of current will create a counterclockwise magnetic field, or one that opposes that one. Okay. And then of course you can play it on, and since both of them are going in opposite directions, you must have different. Oh, ask away. If you have a question, you can ask.
Yeah, like this is what I was talking about. So, like if it's decreasing, they must be all counterclockwise, meaning they support each other.
Yes. Oh, I was talking about the actual currents, not the magnetic fields. Sorry.
Oh, okay.
You see, the actual currents will be in different directions then. The magnetic fields themselves will both, they must support counterclockwise. They must be both, the magnetic fields must be counterclockwise to support each other, yes. But since these two are in different east core, they will be, they are, since they are on the left and on the right of this field, the induced currents will be in different directions to create those magnetic fields. If you use the right hand rule, you'll find out that it will be clockwise for the one in the east. The current will be flowing clockwise, and the current will be flowing counterclockwise in this one. It will be flowing like this for this one, and it will be flowing like counterclockwise like this for this one. In order for you to create counterclockwise magnetic fields. Does that make sense? But the overall magnetic fields themselves must both be counterclockwise or clockwise, the created magnetic fields. Okay, cool. Then I'm going to say goodbye for now and all the best.